Hello, everyone, and welcome back to the Reliability Beat. I'm Sarah.
And I'm Marcus. Today, we are unpacking an engineering mystery that has quietly haunted industrial plants ever since variable frequency drives, or VFDs, became the industry standard. On the plant floor, it's often called the ghost in the machine.
To understand how this ghost operates, we actually have to look at the philosophy of how we run our plants and train our teams. Our site custodian recently wrote a compelling piece on this, sharing a perspective gained from over 30 years in the control room chair. He noted that to a new operator, the PCS7 screen is just a collection of lines and numbers. But to a veteran, those lines tell a story.
Thoughtful. That is so true. In the old mechanical era, that story was straightforward and loud. A pump was a physical beast. When a bearing was failing, it screamed, the pressure sagged, and you could hear the rumble from 50 feet away. The machine talked to you directly. But when VFDs were rolled out, the machine stopped talking sense and started whispering.
Exactly. VFDs brought massive energy savings, but they also introduced a silent killer. New pumps started failing within 18 months, and instead of a loud mechanical rumble, the only warning was a faint, high-pitched acoustic whine and a tiny, almost imperceptible creep in motor amperage on the
Serious. And this brings us to the custodian's why. The core of our training shouldn't just be about linear compliance or following a happy path, SOP, when everything is running perfectly. True capability means having the diagnostic confidence to understand what is actually happening behind the steel and valves when things go wrong. We want our operators to be deeply connected to the physical reality of the machine, rather than just being button pushers who don't understand the underlying systems.
That's a really grounded way to look at reliability. It's about pride and craftsmanship and building deep mechanical aptitude. The custodian talks about bridging the gap between high-level university academics and ground-level, hands-on grit. And to do that at scale, the site has actually developed a fully functional digital twin simulator.
Excited? Yes. It's a consequence-free digital sandbox. Because you can't safely practice troubleshooting on a live, multi-million-dollar process line, this simulator lets us intentionally inject realistic faults, like pump cavitation, valve stiction, or high-frequency bearing currents. Operators get to physically diagnose these issues and build intuitive muscle memory.
So let's use that exact diagnostic mindset today and look at the physics of this ghost. Marcus, what is actually happening electrically to destroy these bearings?
Formative. To understand it, we actually have to go back to 1979. A man named B. Giant Baliga at General Electric invented a microchip called the IGBT, the insulated gate bipolar transistor. It was a massive breakthrough. It allowed us to replace old, high-maintenance DC motors with AC motors that had the exact same precision. It made the AC motor king.
But it was a double-edged sword, wasn't it? The technology that solved our mechanical inefficiency ended up creating electrical destruction.
Serious. Exactly. The IGBTs switch DC power on and off thousands of times per second to simulate an AC waveform using Pulse Width Modulation, or PWM. This ultra-fast switching is highly efficient, but it creates an incredibly high rate of voltage change, what engineers call high dV over dt.
And that rapid voltage transition is what generates the common mode voltage, right?
Serious spot on. In a perfectly balanced three-phase AC system, the sum of the phase voltages is zero. But because PWM switching is imperfect, it creates a high-frequency voltage imbalance between the output phases and ground. This is our common mode voltage.
Okay, so how does this stray voltage get into the physical bearings?
Informative. It couples capacitively. The common mode voltage uses the motor's internal stray capacitances to induce a voltage onto the rotor and shaft. Now, under normal operation, the spinning shaft is insulated from the grounded motor frame by a microscopic film of bearing grease, the elastohydrodynamic lubrication, or EHL, film. Because of this, the bearing acts like a capacitor. The shaft is the inner plate, the frame is the outer plate, and the grease film is the dielectric insulator.
So the shaft acts like an electrical reservoir, building up charge as it spins. What happens when that charge gets too high?
Serious. When the shaft voltage exceeds the dielectric strength of that tiny grease film, which can happen at thresholds as low as 10 to 40 volts peak, the voltage punches straight through. It creates an instantaneous high-frequency arc discharge called Electrical Discharge Machining, or EDM.
And this arc is essentially a microscopic bolt of lightning.
Excited. Exactly. The arc reaches temperatures of thousands of degrees Celsius, instantly melting a microscopic pit into the polished steel of the bearing race. When the molten steel is quenched by the surrounding lubricant, it re-hardens into a brittle spot of martensite. Because this happens millions of times per second, it leaves behind two distinct physical fingerprints.
The first is frosting, where the mirror-smooth bearing race loses its reflective finish and takes on a dull, gray, sand-blasted appearance.
Serious. Yes, and the second is fluting, which is the absolute smoking gun of VFD electrical damage. As the ball bearings roll over those frosted damaged areas, they create a highly distinctive washboard-like pattern of parallel grooves perpendicular to the direction of travel. If you open up a bearing and see that washboard pattern, you know with 100% certainty that the failure was electrical, not mechanical.
Meanwhile, that intense localized heat is also cooking the synthetic grease, right?
Informative. Yes, it breaks down the base oil and additives, turning a high-quality lubricant into a thick, blackened, highly abrasive sludge. So now you have severely damaged steel races running against an abrasive paste. This friction is what causes the motor to draw more current to maintain speed, which is why we see that slow, steady climb in motor amps on our Siemens PS7 screen.
It's a classic electro-mechanical failure cascade. Now, the technical summary mentions certain amplifiers that can make this process happen even faster. Can you explain the reflected wave phenomenon?
Informative. This is a major factor in plant layouts. When you have long cable runs between the VFD and the motor, typically exceeding 15 to 20 meters, the high-frequency voltage pulses hit an impedance mismatch at the motor terminals. The pulses reflect back toward the drive, constructively interfering with incoming waves. This can nearly double the peak voltage at the motor terminals, dramatically increasing the common mode voltage stress.
We saw this firsthand in the plant's investigation with pump P601A, which had a 30-meter cable and suffered rapid bearing failure, while its identical twin, P601B, was completely fine on a short 5-meter cable.
Excited. Exactly. It's a textbook example of cable length acting as an amplifier. Now, another common diagnostic trap is the DC Megger test. When a VFD keeps nuisance tripping on ground fault, technicians will often run a standard Megger test, see a clear pass, and assume everything is fine. Why is that a mistake?
Because a DC Megger test only measures static insulation resistance, it is completely blind to the high-frequency AC capacitive coupling that allows these currents to leak to ground. The Megger says the insulation is healthy, but the VFD's sensitive digital protection is correctly detecting high-frequency AC leakage and tripping the drive to protect the system.
Serious? Precisely. You can't troubleshoot high-frequency AC problems with static DC test equipment. So, how do we solve this? The technical guidelines emphasize that we can't just treat this with a single standalone Band-Aid. We need an engineered, system-level approach.
Right. We have to control the high-frequency current path from the motor all the way back to the drive. And that starts with Layer 1, symmetrical shielded cabling and low-impedance grounding.
Infrastructure. Yes, and this is where we have to banish twisted pigtails from the plant. Because of the skin effect, high-frequency noise travels exclusively on the surface of a conductor, not through its core. A round wire, like a twisted pigtail, has high inductance, which blocks high-frequency currents and forces them back through the bearings. We must use flat, wide-braided grounding straps, which have vastly more surface area and lower inductance. And we must terminate our symmetrical VFD cables using approved 360-degree EMC glands or wide EMC clamps at both ends to create a continuous Faraday cage that safely traps the high-frequency noise.
Layer 2 is addressing the noise at the source, using common mode chokes or output filters. These are engineered filters installed at the VFD output to choke off the high-frequency common mode current before it even reaches the motor cabling.
Excited. Then we have Layer 3, shaft grounding rings. A device like an Aegis ring acts as a lightning rod for the shaft. It uses a ring of conductive microfibers in direct contact with the shaft, providing an ultra-low impedance path that shunts that electrical charge safely to the motor frame, completely bypassing the bearings. For motors up to 75 kilowatts, a drive-end grounding ring is highly effective.
But for motors 75 kilowatts or larger, a grounding ring alone isn't enough because they generate high-frequency circulating currents that loop through both bearings. That brings us to Layer 4, insulated bearings.
Informative. Exactly. We install an insulated bearing on the non-drive end, or NDE, of the motor. This bearing has a thin, plasma-sprayed layer of aluminum oxide on its outer race, creating a high-impedance barrier that physically breaks that circulating loop. But remember, you must combine it with a shaft grounding ring on the drive end, or else you'll simply redirect the capacitive discharge current to the opposite bearing, or the driven pump.
And for extremely critical high-speed applications, we have hybrid ceramic bearings. These replace standard steel balls with silicon nitride rolling elements. Since silicon nitride is a natural insulator, the electrical path is broken fundamentally inside the bearing itself. They cost 3 to 10 times more than steel bearings, but compared to the cost of an unplanned shutdown on a critical line, they are often an incredibly smart investment. Absolutely. Upfront engineering is always far cheaper than emergency repairs and lost production. To wrap up, let's look at the simple daily checklist for our operators on shift. To keep a watchful eye out for the ghost, you want to listen for that telltale high-pitched whine of electrical arcing. Look at the VFD display for ground fault or overtemp warning codes. And DCS check. Trend the motor amperage on the PCS7. If you see a slow, unexplained rise over weeks or months, that is the ghost leaving its shadow on your trend line. And finally, if a bearing is replaced, always ask the maintenance crew, did you see frosting or fluting inside? Knowing if the failure was electrical is the only way to ensure we implement the correct engineering controls so it doesn't happen again. Well, that is a fantastic, practical guide to reclaiming control of our VFD systems. Thanks for joining us today on the Reliability Beat. Stay safe out there on the plant floor. Keep trending, everyone!